If you now look at this equation, it is a simple linear equation, right? Linear differential equation. So, the linear differential equation, if it is oscillating, what stops its amplitude? There must be something to, otherwise its amplitude will grow unless the resistance is exactly 0. If pole is on the right hand side, right half plane, the amplitude will go on going up. If the pole is on the exactly on the omega axis, then you get a pure sine wave. If the pole is in the left half plane, of course, it will be dying down. So, now what I am trying to drive is this amplitude of this oscillator also must be stable, not only frequency. This equation does not tell you how the amplitude is stable. Theoretically, the amplitude will grow going up and up. Something has to keep it stable value. How does that happen? Fortunately, the active device is a non-linear device. So, when the amplitude goes very high, automatically it clips. The gain will fall down. So, because the gain will fall down, the amplitude again readjusts back to a lower value. So, the natural nonlinearity built into this active device will stabilize the amplitude of this. So, if you really want to study an oscillator, you need to model the components inside this as just not linear components only, but you must have a nonlinear model, which will then give rise to what will be your amplitude of the output, stable amplitude of the output. This is what was done in 1927 by a very famous man known as Van der Pol. He was at Bell Labs, Philips Labs in Eindhoven, Holland, and he looked at this problem of triode vacuum tube with a RLC tuned circuit into the making an oscillator, and he studied this circuit including the nonlinearities of the vacuum tube and found how the circuit will behave. He was the first person who has looked at this oscillator the way it should be looked at. Then of course, a lot of people have taken over from here, Minsky, Krylov, Gabulov, umpteen number of names will follow this, but he was the founder of this in 1927 using the nonlinear model of the active device. And he came up with a very interesting differential equation. I don't remember, so I am writing it by looking at my notes. Y double dot minus mu into 1 minus y square into y dot plus y is equal to 0 is the differential equation which he has shown governs a diode, take into account its nonlinearities and a tuned circuit consisting of resistor, inductor, capacitor. The corresponding differential equation which need to be solved to get what is y as a function of time, which we would like to be a pure sine wave with some constant amplitude and constant frequency. Will this give that or not? So, for doing that we need to solve this equation. This I am sure all of you know is a nonlinear differential equation. It is not a linear differential equation. So, because it is a nonlinear differential equation, I do not know how to solve it, as simple as that. So, he tried to solve this, or at least solve it to the extent that he can get some meaningful information regarding the behavior of this oscillator. That is the greatest contribution. One thing is very clear, if mu is equal to 0, which is in some sense the reflection on the nonlinearity of the active device, then it just becomes a harmonic equation. So, if mu is equal to 0, then we will get a sine wave. But if mu is non-zero, then he found out very interesting results. Remember, there were no computers at that time. Today, you will just go to MATLAB and put this differential equation. In few seconds or even less than second, you will get an answer to the behavior of this. But Van der Pol didn't have anything of that nature, nor he had any tables of solution of differential equation mathematicians have derived, because nobody did any work on nonlinear differential equation by that time. So, you have to struggle to find how this fellow behaves. This is available now as a solution in MATLAB. So, you can just plug this equation parameters and it will give you the solution to this. But interesting thing I would like to bring it out is, first time he has thought about plotting the behavior of this by looking at what is called as a phase plane diagram, where you plot y and y dot. What is this diagram? Remember your 101. This is y and this is y dot, they are two state variables, right? So, I am plotting the behavior of the two state variables as a function of time, starting from some t when I switch it on to time infinity. How does this y and y dot vary for various values of t starting from t is equal to 0 to t is equal to a large value? If this differential equation gives you a stable solution, if it gives you a stable solution, at t tends to infinity, what should be y dot? Can somebody quickly tell me? If this is a stable solution, at t tends to infinity, what does stable solution means? Amplitude is stable at t tends to infinity. What does it mean? The derivative of the amplitude is equal to 0, which means y dot must be equal to 0. So, y dot should finally end up into origin as t tends to infinity if this oscillator is a stable oscillator, giving you a periodic waveform of a constant amplitude. Are you with me? Okay. Now, initially it will start somewhere and then go on taking some trajectory, finally landed at this point. If I plot this from this differential equation by rewriting this in terms of the state variable representation and plot this, then during those days, mind you, there is no state variable representation during Van der Pol time. He looked at it in a similar spirit as we are talking about state variable today and plotted this so called phase plane analysis. And he showed that I start somewhere, go on doing like this and finally end up into 0. It is not necessarily a circle, it is some kind of a closed path. This kind of closed path is what he called it as limit cycle. So, if this plot has some kind of a path on which it is ending up into like that, then this is an oscillator. will oscillate. On the other hand, if this path is something like this, going like this, then it is not an oscillator. So, this nonlinear mechanics will give you all this result, but I do not have time, nor am I interested in kind of loading you with all this knowledge. Only thing I want to bring about all this is only to let you know that the oscillator is a very, very tough animal to analyze. And even today we still do not know very clearly how to analyze this, but at least doing numerical approximation, but I do not have any closed form answers. But this is the kind of thing that Jains like him have started with and able to see, visualize what is happening to system like this. Anyway, leaving that aside, it turns out that if mu is equal to some number 0.2, this is taken from internet, if mu is equal to 1 and mu is equal to 5, the waveforms y will be in this case something like this, finally stabilizing to a sine wave. Starts slowly and then it goes up and then becomes stable. So, the mu is equal to 1, it will still be something like a sine wave. But when mu goes still higher, this flow will no longer be a sine wave, but be something more like periodic waveform, all right, but not a sine wave. There is another observation you must make in this. Depending upon the value of this mu, which represents the nonlinearity, if mu is very small, it will take a lot of time for this to stabilize. If mu goes increasing, it stabilizes pretty fast. That means the stable value of the frequency and amplitude will come as mu increases. But if mu becomes too large, then it will not be any more a sine wave. It will be non-sine wave, but still periodic. So, these are the kinds of things which he has been able to visualize and mathematically van der Pol. So, to study oscillators, we really have to find out some analysis like this to see what is the stable amplitude and what is the stable frequency of such systems. But what we do simply in analysis of amplifier oscillators in courses like this is assume that the linear model holds, because that is the easiest thing that we can do. So, we assume that the linear model holds good and then analyze this for linear model and then say that as long as there is a pole in the right half plane or j omega axis, and then it will have a sine wave oscillation. So, this is a very far away from actual performance of the oscillator, because that model will never give you what is the amplitude of the sine wave coming out of this oscillator. It will only tell you frequency will be this, whereas this analysis will tell you what is the stable amplitude you are able to get for the given value of mu, and so on and so forth. So, but we will revert back to the simple analysis in the next class to find out how do I make an oscillator to oscillate at a given frequency. And by this I am not guaranteeing you I give you stable amplitude, because I do not even know anything about the amplitude by this linear analysis. I will only tell you, it will give you oscillation at this frequency. That is true. So, we will tell you how to do that in the next class.